Hello. Today we will see Lab7 DC circuits. We will have two videos for this. Let's start with the first one. So the objectives of this first video is to understand the flow of electric current through different elements in DC circuits, direct current circuits. Secondly, we will prove Kirchhoff's laws, and in the next video we will see how to analyze experimentally the voltage across a capacitor, which is a new element, and we'll see how RC circuits, resistor and capacitor circuits, are made and how to characterize them. So first we will introduce Kirchhoff's current law. That's the first current law. It's first Kirchhoff's law. And it says that the sum of all the currents entering any node or branch point of a circuit, that's where two or more wires merge, must equal the sum of all currents leaving the node. In other words, all the sums entering and exiting a node has to cancel out, must be zero. For example, imagine we have a node A like this in a circuit, and we have two currents I1, I2 having these values, 2 amps and 4 amps. We're wondering what is the value of I3. Okay, so if we apply Kirchhoff's current law, then we know that the sum of all these three currents must be zero. Therefore, if we solve it for I3, we find that the value for I3 is minus 6 amp. This minus means, of course, that the current is reversed and it's entering into the node, not leaving the node. Okay. Second law is Kirchhoff's voltage law. So the voltage law says that around any closed loop in a circuit, the sum of all voltage gains provided by batteries or other power sources and all the potential drops across resistors using Ohm's law and any other circuit element must equal to zero as well. So mathematically, it's the sum of all voltage drops, batteries, etc. has to be zero. So for instance, in this case, we have a loop made out of these four nodes A, B, C, and D, and it's a closed loop with 4 resistors, okay, having these values for the voltage across them. Okay, we're wondering what is the value of the voltage drop across in between nodes B and C. So how do we solve this? Again, we apply Kirchhoff's voltage law, and we know that all these voltage drops has to be zero. So if we solve it for the voltage across BC, we find numerically the value is minus 7 in this case. What does this minus means? Again, that means that voltage B has higher potential than voltage C. So how do we do this in practice? If we were in a physical lab, we will have elements like a DC voltage source, we already know from previous lab, a digital multimeter, also an instrument we already know, oscilloscope, that's especially important for the second part, as we will see when we see the voltage across the capacitor in a second video. We also have the breadboard, and we know what the breadboard is. That's the element that allows us to connect resistors, voltage sources, capacitor, etc. We have field carbon resistors, which are the usual ones we know, and we can associate them in series, in parallel, and we have also capacitors like these ones. So let's start with the first activity. First activity is Kirchhoff's law. What you have to do is to first do a theoretical analysis, and then we'll do a simulation. Okay, instead of having a physical setup, we'll do a simulated setup using special software. So in this case, we want to analyze this circuit having two voltage sources, V1 and V2, having these values, 5 and 10 volts, and 3 resistors, R1, R2, and R3, having these values, 47, 100, 120 ohms. Okay, these are the nominal theoretical ideal values. Okay, how do we mount this? I have here the mounting for you. Okay, this is a picture of the physical setup. Okay, so as we can see, we have here the three resistors R1, R2 and R3, and we have placed here connectors for the voltage source. Okay, we usually use red for positive, black for negative. Here we have another cable for red, and this, instead of black, is green, doesn't matter, for the black negative terminal of this battery. This is the way we will connect V1, having a cable, usually banana to crocodile, for instance, as we saw in the lab, from the voltage source, and the same for the positive, right? And we like to use again the same color scheme, red for positive, black for negative in the source. Similarly, we will connect V2 with the required voltage to the positive and negative terminals within the circuit. And now it's time to do the simulation. To do the simulation, we can run this special software. This is just a web-based platform made by the University of Colorado Boulder, and you can get direct access to this simulator. I will post the slides, so you can click on these slides and you will get direct access to the simulator. This is the way we will simulate, and I will do now a real demonstration on how to operate this simulator. There is no special login username or password. Just click on the web link. You will have this view. This is a view similar to the physical devices. So for instance, a battery is represented like a real battery. Same for a wire, for a resistor, light bulb, etc. We like to use the other mode, this one. This is more circuit approach. Okay. So here you just drag and drop your elements. For instance, a battery like this, you just click and you can rotate it, and when you double click on it, you can see here the voltage. Okay, and you can place within this range from 0 to 120 the voltage drop you want. Okay. You can also place a wire if you wish to extend this up and down. And now, for instance, we can place a resistor. Okay, as you can see, it's quite easy. Just drag and drop, and now there are these elements, all of them connected. Okay. Sometimes it's a little bit funny because it's depending on the size, you can have these nice effects. Now, for the resistor, for instance, you can again change the value here. Okay, and here you can see the current as the real current and the conventional current. We know the conventional current is the one followed by the positive charges, and we know from previous labs that the elements which are really moving are the electrons, which are negative charges. So that's why this simulator is quite nice, because you can see the conventional positive current and the real negative electrons moving. Okay, the speed of this movement depends on what? This is a simulation again, depends on the value of the resistance. The less resistance, the faster things will move. The higher the resistance, the lower the speed. Okay, this doesn't affect to this practice, but this is also good to know. Now, if you want to, for instance, measure I will show you the values for the resistance and the battery. If you want to measure, for instance, what is the current and what is the voltage drop across this simple circuit, well, we have tools like the voltmeter and the ammeter. We have used this already in the lab, and here you have simulations. If you connect black terminal here and red terminal here, you will read, of course, 20 volts, because the source and this resistor are connected in parallel, and in parallel we know that both elements have the same voltage. Now, if we want to measure the current going through this loop, there is only one loop in this circuit, so there is only one current. How do we measure this current? Using an ammeter. And we know that the ammeter, in order to use properly the ammeter, we have to break the circuit. We have to disconnect this circuit, break it, and introduce in series this element, the ammeter. How do we do this? I will just disable this just to make it a little bit simpler. What we can do is, for instance, delete this and connect with a wire from here, from the negative to the positive in the current meter, the ammeter, and here to here as well. Okay, so now we have everything connected, and here, as you can see, you can measure this current, and you want to check using Ohm's law that this current is the right one according to the values we have for the battery and for the resistor. Okay, now your goal is to build within this simulator a circuit similar to the one we are proposing for this lab, and you want to do some things on this. You want to find the theoretical, we name them also calculated values in this table below using Kirchhoff's laws, current law and voltage law. Okay, this would be our calculated theoretical values, okay, using the nominal theoretical values for the resistors and for the voltage sources. Okay, and that would be your second row here. Then you want to measure the values of these corresponding currents and voltage drops. How do you do this? Well, you have to use the simulator, and in order to mimic somehow the real elements, what you have to do is to modify the values of the elements, having a minus 5% tolerance, meaning that, for instance, the first resistor should have a theoretical value of 47 ohms. If you subtract 5%, that means you multiply by 0.95, you will get a value of 44.65 ohms. That's the real value we can associate to a real device like a resistor having this tolerance. You have to do this to all these elements, R1, R2, R3, V1 and V2. And with these values you build the simulator. Okay, your simulated circuit will have these real values, okay, having this 5% tolerance. You want to find, using this instrument, the ohm meter and the ammeter, the voltmeter and the ammeter, placing them accordingly in the regions of the circuit where you want to measure current or voltage, and then you will get these numerical values on the simulator and place it within the table in the measure value, first row. Finally, you want to compare simulated values, which are the measure values, and the calculated values, which are the theoretical values, using the relative error. Okay, and that's it. That's all you have to do in this activity first part.